Ever really look at a snowflake? I mean, really study one up close?
Mm-hmm.
It makes you wonder how nature pulls that off, all those tiny details fitting together perfectly. It's like that with coastlines, too. Zoom in on a map, and you just find more and more coastline hiding in the curves. That's fractals for you, infinite complexity tucked away everywhere. And today, we're going deep on a paper that tackles these head-on, but through this really cool lens, Hölder curves.
Yeah.
Now, I know math words, but trust me, this is good stuff. And lucky for us, we've got our expert here to break it down.
Happy to be here.
So before we even get to Hölder curves, we got to talk about their more, shall we say, well-behaved relatives, Lipschitz curves.
Right. So think of those like the lines you draw with a ruler, maybe a few gentle curves thrown in, but overall pretty smooth, pretty predictable.
Okay, makes sense. But if those work, why even bother with this whole Hölder thing?
Yeah.
What's the problem Lipschitz curves can't solve?
Well, it turns out a lot of shapes can't really be drawn out using just those simple Lipschitz curves. Especially the really interesting ones, like our fractal friends. Those get really wild at small scales.
So we needed a new tool, something more powerful to wrangle those crazy fractals.
Exactly. Enter Hölder curves. These babies can handle sharp turns, sudden jumps, infinite levels of detail, you name it.
No more straight lines, huh? We're talking about mapping out the paths of lightning strikes or something.
Even better. Think about this. There's this famous math problem, the analyst's traveling salesperson.
Oh, yeah, I've heard of that. You got to find the shortest route through a bunch of cities, right?
Yeah.
But with, like, infinite cities.
That's the one. And guess what? Lipschitz curves just weren't cutting it for figuring out those paths through infinite landscapes. But Hölder curves, they were up for the challenge. They could handle all that crazy complexity.
So that's kind of their superpower. They give us a way to map out the truly weird stuff.
Exactly. And here's the best part. Many of the most famous fractals, the von Koch snowflake, the Sierpinski gasket, that crazy Sierpinski carpet thing, they all have a Hölder parameterization.
Meaning we can actually de-draw those shapes using Hölder curves.
You got it. Try doing that with a Lipschitz curve. It'd be like trying to paint the Mona Lisa with just one straight line.
This is what blows my mind, though, this whole zooming in thing. Like, it's not just about tracing the shape, right? It's about what you see as you go deeper into those details.
Absolutely, yeah.
It's about the tangent space of the curve.
Right.
Now, there's another math term, but bear with me here.
Sure.
So imagine you're like ant-sized, walking along one of these curves. What do you see around you? That's basically the tangent space, your little neighborhood on the curve.
Okay, yeah.
And with those basic Lipschitz curves, it's pretty straightforward. Zoom in anywhere, you pretty much just see a straight line, like an endless sidewalk. Not very exciting.
Yeah, you got it.
But with Hölder curves, man, that's when things get wild.
Totally.
The paper calls these shapes you see when you zoom in really, really close weak tangents. And what they found about these weak tangents is kind of mind-blowing.
It is pretty wild.
They can be totally different, even on the same curve. Like, zoom in here, you see a snowflake. Zoom in just a tiny bit over it, bam! Looks like an intricate rug pattern.
It's true, they really can.
Wait, hold on. So each point on the curve can have its own little world of shapes hiding inside it.
Exactly. It's like each point has its own unique zoom.
Mm.
And it gets even weirder.
Oh, no, there's more.
Yeah, so they proved that these different weak tangents, they're what we call topologically distinct.
Okay, now I got to ask, what does that mean? Topologically distinct. It sounds serious.
So imagine trying to squish one shape into another, but you can only stretch or bend it. No ripping or gluing allowed.
Okay, so like I can turn a ball of Play-Doh into a pancake.
Exactly. But you can't turn that ball into a donut without punching a hole in it.
Right, makes sense.
So that's because the ball and the donut are topologically distinct. And the crazy thing is, these topologically distinct shapes, they can all exist within the same Hölder curve.
No way. Just by zooming in at different spots?
Yeah.
It's a game changer. This means Hölder curves pack a ton of information into a single object.
Wow, so it's like that coastline thing, but on a whole other level. It's not just that the shapes look different when we zoom in. They're fundamentally different types of shapes.
Exactly, like completely different mathematical DNA.
Wow. Okay, so now I'm really curious about this example with the two curves, S and C, that you mentioned earlier.
Oh, yeah, that's a good one. So both of these curves, they have the same dimension. Don't worry too much about what that means right now. But they're weak tangents. Total opposites. Okay, hold on. We've got these two curves, S and C, same dimension, but totally different shape landscapes inside them.
Right.
And this is where the paper goes from whoa
Yeah.
to no way.
Yeah.
They actually show us how we would build one of these things.
It's really cool, yeah.
It's like mathematicians playing with a cosmic Lego set, building these crazy complex things.
It is a bit like that, yeah.
And they start with, get this, a square.
Just your average everyday square. And then iteration, elegance.
Okay, walk me through that. What's the iteration part?
So you've got your square, and you've got these two models you can use to change it. Think of them like tools.
Okay, two tools. Got it.
Model 1 is like, imagine a straight line, but you pinch it in the middle. Creates a sharp little point.
Okay, I can picture that. What about model 2?
Model 2 is just a regular, smooth curve, no funny business.
Got it. One with a pinch, one without. But how do you go from those to a whole Hölder curve?
So at every step, you divide the curve up into smaller parts, right? And then for each of those little pieces, you got to choose Model 1 or Model 2.
So it's like flipping a coin. Pinch or no pinch.
Exactly. That's the beauty of it. The super simple choice, Model 1 or Model 2, just repeat it over and over, creates all that wild diversity in the weak tangents.
No way. So like the whole universe of shapes comes from just that one little decision point.
It's kind of mind-blowing, isn't it?
Totally. It's like, you know how DNA works? Just those 4 basic chemicals, but the combinations? Endless.
Exactly. And they don't stop there. They show you can even take this basic construction and tweak it using a technique called snowflaking to make even more insane Hölder curves.
So we've gone from smooth, boring lines to these Hölder curves that are basically universes of hidden shapes.
Yeah.
But where does it all lead? What are the big mysteries about these curves that mathematicians are still trying to crack?
That's the best part. The paper, it leaves us with this really juicy question. Question 1.5, to be exact.
Ooh, intriguing. What's the question?
They ask, could it be that every Hölder curve, no matter how wild it gets, secretly resembles a self-similar set when you zoom in close enough?
So like deep down, are all Hölder curves kind of fractally?
Exactly. It's a question that suggests a deep connection between these curves and the very essence of fractal geometry.
So we're left with a mystery. Do these invisible curves, these mathematical ghosts, hold the key to understanding the shapes we see all around us? The branches of a tree, the patterns in a hurricane. It really makes you think. Sometimes the most incredible journeys, they start with a deep dive into the unexpected.